Alright, hello ladies and gentlemen, I'm glad to greet you all here today, and this is the first lecture of our Natural Language Processing course. Today we shall discuss one of the most famous algorithms, actually mechanisms in NLP and in general deep learning area because attention mechanism actually changed almost everything. It was first proposed back in 2014. Okay, there were several papers. I am referring to the paper from 2014 where it was proposed. But later in 2017, it led to invention of transformer architecture, which actually is heavily based on self-attention mechanism, which also will be covered today. And transformers right now are actually everywhere. In natural language processing, already in computer vision, in graph, machine learning, in biomedicine, in reinforced learning, almost everywhere. So transformers are just the new big thing in deep learning. And today we actually start speaking about them. So let's begin. First of all, I want to make a small recap of the previous lecture where we discussed the neural machine translation and machine translation in general. And we have these two beautiful matrices with words alignment. So we have two languages. Source language is English, target language is French, and we can see that actually every word is being mapped either to one word in the target language or into several words, like we see here. Almost all the time, the word order is just the same, so we have almost diagonal word alignment matrix. But in some cases, like for European Economic Area, we have opposite, just direction in which it's written in French, so zone, economic, European. I don't speak French, so sorry for pronunciation if it really doesn't sound that way. So, just in case, what is word alignment once again? And here we see that if square is white, actually it means that this word is actually being mapped into this word in the target language. Otherwise, if it's black, they're not connected. And when we discussed statistical machine translation, we said that these word alignment matrices were designed by linguists, by people who just by hand created these big dictionaries and just dealt with it. And it was really hard work because it required a lot of human labor and so on. But actually, these two examples are not generated by some people, they're generated by neural network. Okay, by just, okay, not only neural network, just by some model. In general, it might be any model. Actually, they are generated by the attention mechanism. And that's why it's actually called attention. We haven't discussed how it works. Actually, this is the goal of today's lecture. But right now, let's just see that attention is showing every word of the target language to which word in the source language they are actually connected. It actually allows, at the moment of generation of the new word, to see which words in the original language should be actually generated right now. That's kind of it. This is just small introduction, and right now, let's proceed to the attention mechanism. To introduce attention, I actually suggest we first take a look at this picture of sequence-to-sequence model. We already covered it on the previous lecture, so it's one of the main approaches in neural machine translation. It uses two recurrent neural networks. They might be RNNs, LSTMs, GRU, any other fancy stuff. It doesn't matter. So, brief recap. We have phrase on the input, so machine learn is great. So we have some kind of recurrent neural network. At the beginning, its hidden state is empty, nothing in there. We feed into the first token. Actually, we feed into first the start of sequence, then we feed machine, update our hidden state. Now this hidden state is actually updated, and it's mostly based on the machine word because it was updated recently by this word on the input. Then we add learning, take into account previous hidden state, and add this learning word. So this hidden state is somehow based on learned word the most because it is the closest word. Repeat it again, take into account next word, take into account next word, and finally we get this last hidden state which actually encodes the whole sequence we had on the input in source language. So this state encodes the whole sequence, and actually for till this point it's almost the same stuff we did when we just trained our language model in machine learning class when we just generated some speech. So we just take new word, then take new word, and so on. And actually, if we try to predict next word, for example, it will work kind of like language model. Actually, encoder can be pre-trained using language modeling problem. So even ignoring the target language, we can just pre-train encoder to predict next word. and it already will help encoder to at least learn the grammatics and some ways to connect different words in the language. But in neural machine translation, when you have this state, which actually encodes the whole sequence, because actually it's based on the whole sequence we had at the beginning, what do? We actually take this hidden state and pass it to the decoder side, where we have another recurrent neural network. It might have the same hidden size, then we just copy this vector here, and that's it. It might have actually different hidden size, but then it's not a problem. We can just use any linear mapping or nonlinear mapping between encoder and decoder to fit the sizes. And decoder actually works almost the same way as we did in language modeling, but now it starts not with empty hidden state like we did that time, but now it takes the encoder hidden state, takes new first start of sequence token, and generates next word. After that, we can actually use this word as input for the next step to generate next word and so on. We can actually use teacher enforcing, which we covered on the previous lecture, to show our model not only its own predictions, but true words from the training set. That's all true. But if you take a look here, you can see that decoder is always connected with encoder because actually it has taken its hidden state in here. And now every hidden state of decoder is based on previous, which actually on its turn, in its turn is based on this hidden state. So decoder is trying to recreate the information stored in this hidden state, but in new language, in target language. But actually, there is a problem. I guess you definitely see the problem. This hidden state, it's a bottleneck because we use only one fixed size vector to compute, not to compute, to store all the information about the source sentence. And imagine if we have sentence of length 25, 125, 500 words. Then actually, at some point, we definitely will face the situation when we don't have enough space to store all the information because we have fixed size vector, but not fixed size input. We have to fix it somehow. And actually, attention mechanism is the solution to this problem. Just in case, I want once again to recap why using recurrent neural networks and why did we actually come to this problem. Because first of all, when we started speaking about neural machine translation, about NLP in general, we said that texts and actually any other sequences have really specific property. They might have variable lengths, so we might have sequence of length 2, 22, 122, and we should be able to work with any sequence length using the same mechanism. First of all, we just suggested some simple approaches like, all right, bag of words, just combine all the words together and ignore their order. That's true. Then we just switch to some more appropriate methods like recurrent neural networks, convolutional neural networks. But all the time, we were actually somehow taking into account all the information about all the words and then getting rid of the time axis. We can do that using simple average, with summation, with recurrent approach like in RNNs, with convolutions, and then actually, once again, pooling, which is actually averaging along the time axis. All the time, we're trying to get rid of the variable length of the input. Actually, we can do it with attention mechanism as well, and let me show you how to do that. But the main problem right now is this bottleneck, so we want to solve it. So how can we actually give the decoder opportunity to see all the information in the original sentence, not only one hidden state? We could try just give the decoder direct connections to all the hidden states in the encoder, and actually that's it. And here is the main idea about attention. So decoder on each step actually has the direct connection to all the encoder states, and every encoder state is actually representing some position in the sentence, because we have, for example, 4 positions in the sentence and 4 encoder states. And if decoder has direct connection to all the positions in the original sentence, then it means that we don't have bottleneck anymore because we have all the information which was available at the encoder side. So let's illustrate it with the following slides. I guess it will become a bit easier to understand. So let's say we have this decoder state, only one state, and 4 encoder states. And we want actually to get information from all the encoder states. One could ask, why should we really get all the information from the encoder states? Because what is the purpose? Actually, the purpose is, so right now West is here. Right now we're staying at the first step. We're just taking into account hidden state, for example, just some hidden state from recurrent encoder. We have taken into account start of sequence token, and we need to generate the first word in the sentence. Actually, first word is really important because then it will be affecting all the next words because it will be fed into the network and so on. And what if we are speaking about some specific situation when the first word, for example, was in the source language, first word like name or something, it was on the third place. Then actually this hidden state should be connected with this hidden state with the highest weight, and it should ignore all the others. But how can we actually formalize this connection weight and something? Let's just introduce some functional which takes as the input two vectors, encoder hidden state and decoder hidden state, and returns one number. And right now, let's not specify exactly what is this functional, what this functional is. Let's say just it defines some kind of similarity measure, connectivity measure between decoder and encoder vectors. All right? If we have some such functional, then for every pair of encoder and decoder vectors, we can get some number, right? And let's actually do that. So let's compute similarity between this decoder state and first encoder state with second, third, fourth, and now we have four numbers, and we just assume that they are representing some kind of similarity between encoder and decoder. What can we do next? Actually, if we say that they show us some kind of similarity, then we could say, all right, then we want to pick the most similar encoder's vector and use it for the decoder to generate some translation. And actually, I guess you know how we can do that. Of course, we can get just the highest similarity measure from here, highest attention score. So how attentive decoder is to every of these elements. But if you remember, for example, classification, you can remember that we can take logits and then transform them into the probability distribution, right? In here, we propose the same idea. So instead of having some weights, which are not weights, scores, which actually any number from minus to plus infinite, let's first normalize them using softmax and get the attention distribution. Actually, right now, we can see that the third element has the most attention, so decoder is actually paying the most attention to the third element. And now, what do we do next? Of course, we can pick this vector, but actually we see that the first element is also kind of important for us. Why not simply average, but with weights? Actually, that's the idea. So now we can use these attention distribution probabilities actually as weights for our encoder states, and finally get one new updated attention output, which actually incorporates all the information from the decoder, but in one fixed size vector. And then we can just provide it to our decoder and generate next word. So right now, our decoder actually got information, all in the information from the encoder, picked the most important one, and then selected all the information it needed by simply summing up these encoder states with specific weights and taking this information into account. And why I was speaking about bag of words and so on several slides ago. Because actually right now you can see that when we're computing this attention score, we're just trying to use not simple average of the original hidden states, but instead of that, we're trying to use weighted average of the original hidden states, and to compute weights, we actually condition on the decoder state. So actually, attention is just approach to compute the weights with which we should average our hidden states of the encoder. So these hidden states are summed up, averaged in the best way for the current decoder state. So now in here we have all the necessary information for this particular decoder state, concatenate in here, generate next word. What would do next? Put it here, get next hidden state, compute new attention scores, because we now have different decoder state. It has different scores, you see. We have different attention output. We generate next word and repeat it again, and again. So, main idea of attention is just to compute how similar, how important is current decoders, how important are all the encoder states for the current decoder state. And actually, that's it. And just to clarify, right now we're speaking about modification of the original recurrent network sequence-to-sequence structure. So actually, because we changed the architecture of our network, it now will start training in a bit different way. So now actually every hidden state won't just represent the left context of the phrase we already had. Actually, it will represent something a bit more complex. Okay, in here actually it will, in here. No, while we're training, sorry, 1, 2, 3, yeah, every hidden state will not just represent the left hidden context of the whole phrase, because when we speak about it, we can actually see that now our network is already getting gradients not only from decoder side via this connection, but via the attention as well. We'll actually see it again and again, and it will become more obvious. What I'm trying to say is that please don't be careful with your intuitive explanations what's going on, because right now, what did we say? We said that every hidden state is actually representing some position in the text. That's kind of true. Then we said that we define some similarity computation operation between our hidden state of the decoder and encoder and compute these similarity measures. Actually, they named attention scores. Then we just normalize them to average hidden states of the encoder and the weights are conditioned on the decoder. And then we just repeat it to generate better translation at every step. Here it is. So here is the basics of attention mechanism, and now a bit more mathematics. So here is the same stuff, but now with formulas, not with pictures. Let's denote encoder hidden states from H1 to Hn, and encoder hidden states from H1 to Hn, and one unique, right now only one fixed decoder hidden state at time step t, st. Just in case, right now we assume that they both are in the same k-dimensional space. Of course, we can update it, make it better for different dimensionalities as well. But attention score can be computed different ways. We just said that it should be a functional which takes two vectors as the input and gives us one number as output. We can define it different ways, but the easiest way, I guess, is to use simply dot product. And it is kind of intuitive as well, because remember what we discussed when we were speaking about the word embeddings. Dot product is actually multiplication of the norms of these dot products, of these vectors, by the cosine of the angle between them. But when I was speaking about hidden states, we can remember that they are generated using these tangents or hyperbolic tangents, also sigmoid operations. They have such activation functions. So the norm of the vectors of the hidden states should be really kind of close to each other because they are restricted both on the top and on the bottom. That's why all the norms are rather similar to each other of the vectors. And when we compute the dot product, we actually focus on the cosine similarity between these vectors. And then actually it's kind of intuitive. Why? Because let's get back to the original picture we had in here. These are exactly the attention scores, normalized attention scores, visualized. We can see that actually every word is paying the most attention to its origin in the source language, and that's it. Actually, our network learns how to connect different words, meaning the same in different languages, and attention is capable of that. So here we go. First word is mostly focusing on the Z, agreement, accord, on, sur, the, la, don't speak French. European economic area, actually European, but it's on the different position, but actually it doesn't matter right now because attention is able to attend all the position at the same moment. Actually, it can understand that different words are actually somehow connected to this particular word node, like covent, der, notaire, fair. Really hard to read it. So attention is just giving us an opportunity to read to get attention to all the positions at the same step. So we computed the attention scores, similarity between one decoder state and all the encoder states. And then we just compute the softmax over all these attention scores to normalize them. And then we just use simple average, weighted average, not simple average, of all the encoder states to get the attention output. And then this attention output is actually based on all the encoder states, so it somehow has an opportunity to have all the information from the encoder conditioned on the current decoder state. That's kind of it. And attention provides both interpretability, because right now we can see what the decoder was focusing on at every step. And we get word alignment for free. Now we don't need to call just hundreds of linguists to generate new word alignment matrices for new languages and so on. It's enough just to have some parallel text corpuses like Wikipedia, for example. And that's it. But attention provides not only interpretability. Here is another really important just highlight from this paper which actually proposed the attention variant we're discussing right now. It was named neural machine translation by jointly learn to align and translate. And here is the result actually. Here is the sequence length varying from 0 to 50. And here is quality of the translation, which actually increases first when sequences are about 10 to 20 lengths, and then the quality of the translation decreases, and decreases actually significantly. It happens because the hidden state is just too small to capture all the information, so the network is actually unable to capture all the information, and it affects the quality of the translation. And increasing the size of the hidden state is actually not the good idea as well, because it will cause our network to be more capable of overfitting, so it will just be ready to start overfitting quicker. So we have to balance it. But when attention came into the place, we can see that actually quality of translation stopped to fall down to degrade when we increase the length of the sequence, because now we have no bottleneck at all. Decoder can attend all the position in the encoder at every step, and that's kind of not a problem. That's the property of this architecture. But of course, I guess you can understand it. Even if we have such great, just tremendous results that now we are able to work with any length without losing any information, we have a price to pay for that. And actually, a price is literally on the slide. You can see it on the right part of the slide and on the previous slide as well, because attention is actually quadratic in terms of computations, memory, and so on. Because right now we have to compute attention of every word, every position in the target language to all the positions in the source language. So actually, if we assume that our lengths of input and output are equal to n, for example, then we have to compute n squared number of attention scores to translate only one sentence, compared to just simple sequence-to-sequence model, which actually required only 2n operations, which is much quicker because it's linear, and with attention, it's actually quadratic. You can see it actually from the screen, I guess, kind of obviously. So there is a price to pay. Attention is much slower compared to just sequence-to-sequence modeling without attention, using simple RNNs, but it still provides really huge improvements. It provided them back in 2014 already, and nowadays actually it's just almost impossible to find some new models which are showing really comparable results with attention-based models without attention. And I hope now you have a bit better, broader view on the attention mechanism and understand how does it work. Of course, attention mechanism is not only based on the dot product, it's just one of the most obvious ways to compute the attention, and actually it's similar to what we discussed when we spoke about word embeddings, so that's why we use this example. There are, of course, different ways to compute the attention score, like basic dot product. Here it is. It's already here. Actually, we can use some kind of linear mapping between encoder and decoder states using some metrics omega, W, or omega, just the way you name it. And it actually helps us in two situations. First of all, it allows us to compute some kind of more complex attention score, and it also allows us to compute attention score even between different sized vectors. For example, our decoder has 10-dimensional vector of the hidden state. Our encoder has 15-dimensional vector of the hidden state. So actually, we need first to map them into the same space. Actually, this omega is mapping this state of the encoder in some linear space where they actually being multiplied using dot product with the decoder hidden state. Or there are even more complex techniques like additive attention, for example. Actually, if you look here, you can see that it's really close to some kind of neural network. Actually, it is a two-layer neural network. We have first linear transformation of encoder, of decoder, then we have some kind of nonlinear activation, then we have some kind of another multiplication by vector v, and finally we get some result. But all the time, just we can have different attention variants, but all the time we're speaking about just functional, which is mapping two vectors into one number. And we assume that this number should represent some kind of similarity. And once again, the beautiful part. We even don't specify explicitly what should be this similarity. Of course, in dot product, we speak about cosine similarity and so on, but in here, what kind of similarity we are speaking here? Actually, it's not that bad because we allow our network to find in which form it should represent the hidden states. So this similarity measure would be optimal to reduce the loss. Actually, network is learning by itself to find the optimal representations in the hidden states because it's able to change the weights of the encoder, decoder, and so on. And it's able to change the weights of the attention if it has some too. So we kind of just give the architectural property of our network to learn similarity between different positions and then just leave it to do the job. And that's kind of it about the attention. I hope right now it's a bit more clear, straightforward, and you have a bit more intuition about the attention. And right now I suggest you just maybe put the video on pause and just think for yourself, once again, maybe run through the slides. So is it clear? Why do we need attention? Just in case, I repeat it once again. So we need attention to have an opportunity to attend all the positions in the source sentence, speaking about them in terms of encoder states from every position in the decoder, ignoring this bottleneck we had before heuristic. So right now we have an opportunity to bypass this bottleneck, and that's really great. Okay, so I hope right now we have a bit better feeling that you understand what's going on, and we can actually proceed to even deeper variant of attention mechanism. Actually, it's almost the same, but it was proposed almost 3 years later in 2017. So we shall discuss it right now, and it is named self-attention. And yeah, speaking about self-attention, I hope you really pay attention to yourself as well, because it's really important, especially nowadays. So, speaking about self-attention, get ready, we move on. Self-attention at high level is exactly the same concept of attention, but applied to the sentence itself. So what I'm trying to say? Here is a sentence, for example. The animal didn't cross the street because it was too tired. Why should we actually use some kind of neural machine translation and use some kind of decoder to understand, actually, why should we use some kind of decoder to use the attention mechanism? Because right here, attention could be really useful. For example, here are several questions. What does it in this sentence refer to? Does it refer to the street, to the animal, to cross, to what? And what if we ask the attention mechanism, actually self-attention mechanism, for this, we ask this question and try to use self-attention mechanism. So on the high level, at the high level, just self-attention is just attention mechanism, but applied from sentence to itself. So it is actually the method which is one of the core methods of the transformer architecture. We'll cover it on the next lecture. And self-attention is being used to understand the ways of the connectivity between different words within one sentence. And actually not only words within sentence, but any structured elements within structured input with each other. Like patches in images, like nodes in graphs, like words in sentences, and so on. Like some sounds in speech, for example. So let's dive deeper. Here is it, for example. Here is visualization of the attention scores. Once again, we already discussed them. From word it towards the animal, we can say actually it is the highest connection. The most attention is paid to the animal. It, the animal. Actually, it's kind of obvious to us. So it is the animal, and it is actually referring to the animal. But we also can say that it was too tired. Here is actually the second part of the sentence. It was too tired. So it was too tired. Another property, connection with it. So how can one actually learn this from scratch? Actually, to do that, we need only two things. First of all, we need to formulate mathematically the way to measure similarity between, not only similarity, but connectivity between any two elements of our sentence on the input. And second, we need to define some kind of problem where we will be able to train all the weights, or to fine-tune all the parameters of our model to make this algorithm work. Actually speaking about the second step, about training it and finding the optimal problem, we'll speak on the next lecture. Today we'll only briefly capture it, but speaking about the technical, mathematical way to measure the connectivity between two elements, it's about today. So, here we go. Let's say we have simple phrase, thinking machines, and that's it. And let's, of course, say that we already use some kind of embeddings, like word-to-vec embeddings, for two words, thinking and machines. Now let's introduce several concepts. For example, when we're speaking about attention from the sentence to itself, we can at least formulate several constraints. First of all, this attention should be directed. So actually, animal, didn't, and didn't animal, they're connected kind of with different questions. For example, animal did what? Didn't cross the street. Didn't cross the street. Who? The animal. So the attention should be directed. Otherwise, it just will have the same connectivity between animal and didn't an animal. It's kind of bad. So let's say we're just trying to answer different questions using our self-attention. And second, when we formulated that our attention is directed, we can understand that we can't use just simple dot product, for example, like we did in just attention, because in there it was always directed from decoder to all the encoder states. But right now we're actually speaking about encoder to encoder attention, so we need some kind of direction. That's why, let's say we have two specific vectors for every word. It's query and key, and it's just the same stuff like you see everywhere in computer science. So query is actually from where we're looking. So we have query thinking, and now we want to compute its attention to word machines by attending the key vector machines. So just in case, these are just names used, proposed in the original paper from 2017, attention is all you need. And query is just vector representing the word from which we're watching the next word. And key is the vector representing the word we're looking at. Okay? One could say, wait, we have three vectors here. We have also values vector. What's that? Actually, that's also really, yes, straightforward. So we have vector for every word. If we look from this word into another word, we have key if we look on this word from somewhere else. And also we have third vector, which is actually used just to represent the meaning of the word. One could say actually that we can use the original embeddings as well for that. You're right, but authors proposed to use three vectors from where to where, and what do we see? Three vectors. And I guess it's kind of obvious how we can compute these vectors. We just use three different matrices and just map this original embedding into query by multiplying vector by this matrix, into key by multiplying by this matrix, and in the value. That's kind of it. What do we do next? Actually, we can compute, after we created query, key, and values, we can compute the attention scores between query and key. Here it is, first attention score. Here is second attention score. Then normalize it. Actually divide by 8, square root of dimensionality of these vectors to reduce the variance. We can discuss it on the webinar, for example. Then normalize it using softmax. And now we actually have these weights with which we actually sum up our value vectors. You see? And now we have this vector Z1, which is actually representing the whole sentence, but from point of view of the first word. So actually, what we have here, Z1 is actually representation of the whole sentence, because actually it includes vectors from all the positions. But if we look at the whole sentence from the first word, same stuff with Z2, it was generated by the same procedure, but here we used query 2 multiplied by key 1 and key 2. So we had different weights for value 1 and value 2, and we summed them up with different weights and got Z2, which is also representing the whole sentence, but from point of view of the second word. That's it. Okay? So let's just somehow overthink it and get back once again. So what are the query, key, and value vectors? Just once again, they're just abstractions that are useful to calculate and think about attention. So they're just abstractions. They don't have any specific meaning. We just assume that if we give our network an opportunity to decompose the information into three parts, which are intuitive, rather intuitive for us. So from where we're looking at the information to what information exactly we're looking and what do we actually see there, we think that it will actually somehow help the network to learn the parameters a bit better because it has some kind of informative prior in terms of architecture. Actually, we incorporate this prior into our model. And that's kind of it. So we have representation of the whole sentence from the point of view of the first word, from the point of view of the second word. What do we do next? Actually, we use these representations of the whole sentence for any kind of purposes. Because right now we actually have some kind of average of all the words in the sentence, but from different positions. How do you think? What could actually make this mechanism even better? And yeah, just in case, why this mechanism is actually great? For two reasons. First of all, now instead of using simply vector to represent every word, we use a vector to represent not only this word, but the whole sentence. But this representation is heavily based on the word on the position we were staying at the beginning. Second, we had some vectors on the input, actually two vectors in this case because we had sentence of two elements, so sequence length was equal to 2, and at the end we also have two vectors. So actually nobody prohibits us to repeat the separation again and again and again and again, and actually that's what will happen. But actually I have one additional comment for you, and let's first take a deeper look how it's being computed. So first of all, everything we're speaking about right now is really effective in terms of computation because we're speaking only about some matrix products, and I guess you know that our computers, especially GPUs, are really capable of matrix multiplication. We're actually using it all the time, and they are really great at that. So we just pack all the words in the original sentence into some kind of matrix, then multiply by omega q to get query vectors, by omega k to get key vectors, omega v to get value vectors. That's kind of straightforward, I guess. And then we just multiply these matrices by each other once again, compute softmax, multiply by the values matrix. Please, in here, I guess, if you have some feeling that something is running away, just pause the video and try it on the paper because it's just matrix multiplication, but still, at the first time, it might be a bit non-intuitive. And we get the result just by sequence of several linear operations. Again, non-linear speaking about softmax. So it can really be computed quickly using our machines. And actually, we have one additional question, which we asked really at the beginning, when we said that actually different words might have different connections with each other. Like animal is actually it is the animal, but it also has some property, it was two-tied. So actually it should be connected with two-tied as well, but we see that this connection link is relatively weak. And just in case some of you might have already seen that we have somehow empty right part of the slide, actually that's not just bad design, that's because we need to have something here. Actually, we can ask different questions from different words to other words, and that actually really beautiful concept for the self-attention, because we can just use one attention head, which actually represents some type of connection between this word and between all the words, actually. But we can actually use another attention head, which will learn different questions, different connectivity between the words, and to do that, we only need three new matrices. Another matrix for queries, another matrix for keys, and another matrix for values. And actually, we can have several attention heads, which are completely independent because we just randomly initialize these matrices. After that, they are being trained independently. And in the end, for example, in the original paper, authors proposed using 8 attention heads. We can have 8 different independent in terms of parameters representations of the original sentence. And once again, all these representations are preserving the sequence length. So instead of getting rid of the variable length of the input, right now we just preserve it all the time. That's kind of fine. So all right, we have 8 attention heads. But actually, if we, for example, had this vector of size 128 multiplied by 8, it's actually really long. It's actually 1024. So kind of not so convenient, right? So we can just then average all these vectors or just sum them up with some weights. And these weights, once again, might be just learned by gradient descent. So we have all these representations from all the heads. We just concatenate them along the feature axis. So we still have length of sequence 2, and first element of the sequence is actually represented by this concatenate vector, second by this one, and then we just multiply it by some kind of matrix. And just in case, pay attention, this matrix size does not depend on the length of the input. So if we have input length 2 or input length 122, this matrix won't change because it's just mapping these 3 by 8, 24 elements on this picture into 4 elements. So it's just some kind of linear mapping from 24-dimensional space into 4-dimensional space in this particular case. So we preserve sequence length all the time. And it's the most beautiful part because right now we have several attention heads. For example, here is the visualization of different attention heads. Here is the first one we discussed before. Here is actually the second one. We discussed it right now. And right now, every attention head is capable of its own way to connect different words. Of course, one might say, why should these attention heads actually learn something intuitive, because we don't ask them explicitly to do that. But that's actually the magic of deep learning. We only design the architecture which is suitable for this particular problem, and then we just train our model using data. So the gradient descent actually forces the parameters to take some appropriate values to reduce the error. And because this prior we proposed in here that different words might be connected using different ways is really informative, our weights are just being tuned so the error lows down, and actually it leads us to such attention heads. And just in case, another way to interpret it for yourself, just another analogy, remember what do the convolutional neural networks do. We have different filters. All the filters are actually, or kernels, all the kernels are actually independent from each other. They're just initialized with random numbers at the beginning, and then we train them simultaneously and completely independently. And they learn different patches from our image or from our text if we're using convolutional neural networks with text. Actually, when we speak about attention heads, it's exactly the same situation. Right now, we're using different heads which just focus on different information, because if they capture more information, they will deliver lower error and actually the goal of gradient optimization. So that's it. We just give an opportunity for our model to find the optimal parameters, and it does all the rest. Okay, we can add any regularization, updates, constraints, and so on, but still, it's just not so useful to have all the parameters the same for our network, because by using different parameters, at least it can all fit better to our data to reduce the loss, and actually reducing the loss is the main goal of our network. So actually, here is the attention mechanism. Here is actually it's visualized from the beginning to the end. So X on the input, then 7, 8 attention heads, and Z on the output. And if you can see, once again, Z and X are completely of the same size, of the same shape. So the beautiful part of the attention, self-attention, is actually we don't change the size of our input. If we had sequence length 12, now we have sequence length 12, but now every vector is not representing only one word, but it represents all the information in the sentence from the perspective of this word. And I guess you understand that after that we can just use another self-attention layer, which actually will make these vectors even more generalized on the whole sequence. Then we can do it again, and again. Actually, in the original paper, authors, I guess, used 6 self-attention layers step by step. They had some non-linearities between them as well, but still it can be repeated many times. And just in case, here is the visualization for multi-head attention. So different colors represent different questions. For example, I Who kicked? Who? I. Did what? Kicked. Did to whom? To the ball or kicked what? The ball. So attention head 1 is about who. So kicked actually looks at I the most because who kicked? I kicked. Attention head looks at the question did what? So kicked is looking at itself. Yeah, every word can look at itself as well. And attention head 3 is looking for the question to whom, for example, or to the question what, and it has a connection to the ball. So here is the main difference. Attention is just a weighted average, and multi-head attention is actually weighted average of weighted averages, if it can be said this way. So we use different weights, which actually represent different ways of connecting the words, and then we average all the results in the end by multiplication by this huge matrix. Okay, kind of that about self-attention. Of course, it might be not so straightforward from the first time, but actually that's fine because this is one of the main results in deep learning area from 2015, I guess, because it was proposed in 2017. So it was really great. And of course, it takes some time to understand it, but the concept is relatively simple. And just a tiny outro for the next week, where we start speaking about the transformer, because actually self-attention is a core mechanism which is staying in the fundament, in the basics of transformer. So just beautiful picture of the transformer. Yeah, nothing interesting here. Actually, transformer contains encoders and decoders. At this point, actually, it looks like exactly the same we have seen, exactly similar, really similar to the sequence-to-sequence models we had at the beginning of this lecture. But actually, encoder is actually a sequence of absolutely same in the architectural terms encoders, and every encoder contains self-attention layer, which is actually the most important part. Here are the outputs actually, and it has some just feed-forward network where we have some dense connection and non-linearities, and some skip connections as well in here to make it a bit more stable, but it will be covered on the next lecture where we speak about the transformer. Otherwise, the main idea of self-attention is that every word not throws, but flows through its own path in the encoder, and we preserve all the positional information in place all the time. That's kind of beautiful. And here is tiny outro. So, attention mechanism is general, and it allows us to attend all positions in the original sequence or in the sequence itself if we're speaking about self-attention. And main idea about attention is that now we're able to explicitly compute measure of importance of every element for every element. That's it. So if we have two elements, now we can actually compute how this element is important for this element and vice versa, and it can be directed. That's important. And that's why actually attention is useful in all the areas. Because when we speak about graphs, we have different nodes, and they are actually somehow connected with each other. When we speak about images, we can separate image into different patches, and these different patches are actually somehow connected with each other. Here we see the dog, here we see the ball, here we see the duck, whatever. In sentences, it's kind of obvious, I guess, after this lecture, and so on. But there is a price. Attention mechanism is quadratic in terms of time and actual memory, and it requires more computational resources compared to just linear approaches, like linear in terms of complexity, I mean, like simple LSTM and so on. And one of the most important ideas from this lecture is that actually the changes we make to the model architecture, like taking LSTM and LSTM in sequence-to-sequence modeling and adding the attention mechanism to it, these changes affect the way the model is being trained, so our intuitive explanations might be kind of really out of sight, because when we change the architecture of the model, we actually cannot assume that the encoder and decoder are still learning the same stuff they used to learn without the attention. But still, our intuition is a good instrument. Just please be careful using it. Okay, so here is the brief outro. Attention allows us to attend all the positions. Self-attention allows us to do that even within one sentence, ignoring all the decoders, encoders, and so on. Actually, I guess you right now can already understand what we can do even with only encoder. For example, we take only encoder. We have some kind of vectors on the output, and let's say then we just want to solve some classification problem. So no decoder is needed. Then, for example, can take either average of these vectors on the output, or can always take only one vector, for example, from the first position, which is actually, we don't have it here, but usually we have the start of sequence token at the beginning. So for example, we can take only start of sequence token output at the end and use it as vector representation of the whole sentence. But right now, instead of reading it from the left to the right or from the right to the left using recurrent neural networks or using global average or maximum pooling like we did in convolutional neural networks, we actually have the weighted average of different representations of the sentence with weights which are actually conditioned on the meaning we have at every position. So the attention is actually, self-attention is kind of the most general from the approaches we discussed right now, because right now we can take into account all the positions in the text at the same time, and actually condition on the left, right context on every context we have. So, all right, here is the outro about attention mechanism. I hope now you have feeling that you understand it. If you have some questions, any questions, please ask me in the chat, in the web, on the webinar. Ask each other. Actually, highly recommend to read this beautiful post by JLMR. Actually, many illustrations in this particular lecture are based on his great blog post, because I just love these illustrations. They are really great and they really help to understand what's going on. So please take a look at it. We haven't discussed the transformer in general, so it might be not so straightforward because transformer will be covered on the next lecture. But otherwise, it's still a good read. So thank you for your attention today. I hope it was useful and interesting, and see you next time. Take care.